Welcome to another data science deep dive on our technical track. The following presentation is by Subhabrata, Majumdar, senior inventive scientist at AT&T Labs Research, and she's going to be sharing his presentation on a framework for industrial uses that address their organizational, methodological, and mechanization needs. He will also talk about their approach and how it benefit from prior experiences handling security and privacy concerns, as well as part internal machine learning projects. Enjoy the presentation.
Hi everyone, my name is Majumdar, and today I am going to talk about a system to integrate fairness transparently, especially an industry approach. This work is developed jointly with Emily Dodwell, Cheryl Flynn, Balachandra Krishnamurthy, and Ritik Mitra, who are my colleagues in data science and AI research organization of AT&T. And what SWIFT is in a nutshell, an operational framework to integrate fairness considerations, bias monitoring into enterprise settings in a transparent manner. Just a little bit of disclaimer, the examples that we present are not representative of any actual AT&T use cases or AT&T processes. This is a theoretical operational framework. A little bit about bias and fairness in machine learning. I'm sure a lot of you have heard about, have been part of such conversations in the recent past. It is actually ubiquitous across different types of applications of machine learning. Pedro Domingos, a famous technologist and computer science professor, he mentions in one of his books that people worry too much about how computers will get too smart and take over the world. But the real problem is that they are actually too stupid, and the computers have already taken over the world. This is because the machine learning systems are trained to ingest data that we humans ourselves create and then feed back the results to be deployed on us to influence our own actions. Sometimes in that process, these deployed machine learning systems learn to perpetuate already existing social or economic inequities, or even create new ones, and then scale up to a level that has never been done before in human history. The impact of this on real people is undeniable, especially in marginalized communities. On the other hand, industries also can't go scot-free always. The impact for industries, the risk for industries lies in things like tarnished brand image, high remedial or regulatory cost, so essentially tangible monetary risk. Moving into some examples of bias problems that surfaced regarding machine learning systems, the famous Amazon hiring example, just take that as an example. Since the early days of Amazon, most employees have been or were males, employees skewed towards males, the population of them. And when Amazon decided to try using machine learning, try training a machine learning model to screen applicants for future job positions, what happened was that the machine learning system sifted through this large volumes of data and learned to just select male employees, because historically most of the employees have been male. So, hey, they must have been doing something right. So that was its obviously wrong logic. The second example was the Facebook housing discrimination example, which happened when Facebook allowed advertisers to select target populations for showing certain ads to by themselves. And what happened was that for certain groups of housing ads, some kind of redlining happened. These ads were being targeted to populations which were disproportionately leaving out minority groups. And thirdly, the Netflix thumbnail example, where the thumbnails or cover images for suggested shows, Netflix decided to do A/B testing, set up a system so that different thumbnails are being shown for the same content to different people. And what happened was that for this specific show, Black viewers were shown this thumbnail, in spite of the fact that none of the main characters of this show, like Father, were actually Black. So there is an obvious problem, the reason for which we don't always know, or those who have deployed them don't always know, or they were not aware of before these problems came to surface. So that's kind of a reactive approach, if you will, to detecting and mitigating such problems. And obviously, these kind of approaches were inefficient in handling the issues. This is where SIFT comes in. SIFT focuses on this problem of fairness at all stages, specifically before deployment, even starting from the data gathering process in the machine learning lifecycle. And we aim to cover it, a gap in the existing literature, which is that how to do this thing in an efficient manner in an enterprise setting. And SIFT does that proactively as compared to the current reactive approach, where you know that there is a problem only when other people find out about it and it's too late to mitigate that, to already undo the damage that has been done. So what we want to do is for machine learning pipelines to be prescient of problems even before, while working on the data gathering and model building itself. And we do this using, actually reusing lessons from the past, specifically on how security threats have been handled, how internet security threats have been handled. More specifically, what we do is we reuse lessons from past projects in the same company. So this is kind of on the similar grounds as the concept of signatures in internet security, where you use signatures or salient features of past attacks to identify similar future attacks. Finally, to round out the introductory discussion in this slide, SIFT is the first attempt to propose a framework that efficiently brings together the research that's mostly been done in the academic community in terms of detecting and mitigating bias in machine learning problems in the industry context. Moving on to the key contributions of SIFT, our key contributions are threefold. Firstly, we propose a framework which is a technical JSON-like stepwise schema to store data, model, and bias history of a project. So essentially, you know that what has happened in a past project, including what bias considerations were given, what bias detection algorithm was applied, what bias mitigation algorithm was applied, was there mitigation done, and what considerations did the people who worked in the project took into thought before actually deploying that, before actually proceeding to deploy anything based on that machine learning model. Secondly, we take this information from a large number of past projects, and we expect an enterprise to kind of keep track of past projects for this purpose. We take that information and reuse that stored information for informing future projects, for informing the bias monitoring of future projects. And what that does, it amortizes the cost of such kind of monitoring. So bias monitoring is some extra work that is being done by a project to kind of prevent these kind of PR problems or other regulatory problems, brand image problems from happening. And since we kind of keep on reusing the information from past projects to inform future projects, we expect the average cost to go down as time goes on and more projects go into the past projects database to kind of inform more future projects, so that this extra cost of bias monitoring becomes less and less as time goes on. So we essentially crowdsource prior information and knowledge from across the company and to lessen the cost of bias monitoring. And thirdly, this is also novel in the sense that we tell the machine learning practitioners that are working in a project that exactly at what steps of the pipeline do they need subject matter expertise. Does a human need to come in to see that, okay, the risk is too much, stop here, or okay, fine, you can go on and deploy this product, these kind of formalizations. So essentially this embeds company values in machine learning projects pipelines through pre-established guidelines from the actual stakeholders that know much more about the project and how it's going to impact real people, how it's going to impact the customers of that specific company than the data scientists themselves. In a sense, what we are talking about is a 360 view, of having a 360-degree view of the fairness landscape inside an enterprise, so that you know exactly what has happened in past projects and what is going to happen in future projects based on those past projects. So you use the information in past projects to inform future projects, and then the future projects again go into the project's database to inform more future projects. So that's the basic idea of SIFT. Going into the technical details now, we have a number of SIFT objects, starting with a SIFT project, which is a top-level object that we propose would be initialized for every machine learning project inside a company. In the beginning, it will have a project description and a data location for the initial data set that the project is beginning with. And as time goes on, the different components of that will be populated. And what are the different components? So the next level components are 3 additional objects. These are also initialized and then populated as the project goes on. Firstly, SIFT data that has different components like data location and metadata, who is working on the project, who is the project lead, what's the role of each of these people, things like that. Model history. This tracks the history of the machine learning model that is being used through development and testing. So it contains things like what is the proportion of split, train, test, validation split that was used, what is the random seed that was used to create these splits, what is the algorithm used, the list of tuning parameters, hyperparameter values, and the performance metrics at these hyperparameter values, things like that. So all the nitty-gritties of all the technical nitty-gritties of model building that can be stored over here. Firstly, and this is thirdly, and this is the most important component of SIFT, is the bias history component. So there have been developments in the literature which propose things like data sheets or model cards by Google and IBM companies, research divisions of such companies that kind of have artifacts to codify different aspects of model building that is similar to SIFT data or model history. But bias history is novel. There is nothing like that, like bias history anywhere right now. And what it does is it tracks all the components related to bias in a machine learning project. It tracks each stage in the bias detection and mitigation process. So step 0, bias was detected using X algorithm. It gave Y performance metric, things at that level. Step 1, mitigation was done by XX algorithm. After mitigation, bias metric gave value YY. So that much detail. And in future projects, you may or may not want to use information at such detail. But given that you want to use such information, that information is already there. That's a big efficiency gain in terms of an enterprise setting. So essentially, this gives transparency on how fairness is weaved into the machine learning lifecycle for everyone in future to see. If tomorrow some company that has SIFT runs into some PR problems related to fairness, they can actually show that they have done the possible vetting if they have all these steps recorded. And thus, that kind of gives a defensible ground for them to stand on, given that they have done these necessary vettings of fairness-related risks. So that's kind of the idea, that the storage and reuse of fairness-related considerations. And as I have mentioned right now, it enables the reuse for future projects that not only is there if you need to use, but it kind of lowers the final cost of future projects as well, lowers the cost of doing similar things in future projects. You don't have to start from ground zero. You don't have to start from point zero from future projects. You always know that, oh, okay, similar projects in our company in the past have done this. So that's why we should probably do that. So these kind of thought processes would be facilitated using the SIFT kind of framework. Now the SIFT pipelines. SIFT has 4 pipelines. The first one is information gathering, which is essentially you start a project, you collect some data, and now you're ready to move on in actually building the model. So what we do in this part, the most important part here is the similar project and sensitive feature identification. So you go through the past projects, the list of past projects that have already been stored. You go through their information, either manually or using simple semantic search procedures, and find out that what projects was similar. And by consulting with the description of those projects and with some subject matter experts, you identify sensitive features. And then before proceeding, you assess the risk of proceeding based on the information from past projects and the sensitive features. Nextly, pre-model. In the pre-model, you basically prepare to fit the model. So prepare the data, build your features, clean the data, standard data science procedures. Apart from the standard procedures, you also aim to identify certain bias-related things. For example, proxy features that are highly correlated with sensitive features, or group of sparse samples or marginalized groups corresponding to any of the subgroups of the sensitive features. And after detecting this, you again do a risk assessment. So this part is important. This risk assessment part is important in the sense that after each of these pipelines, you do a risk assessment to see that whether, in light of the new information of the previous steps of this pipeline, whether it is safe to proceed to the next pipeline. In the third pipeline, we actually fit the model-involved pipeline, and this is kind of similar to what has been proposed in the machine learning literature right now. So essentially pre-processing, in-processing, post-processing algorithms. There are a lot of algorithms right now. Many of you might have heard of the IBM AI Fairness 360 library, which has a bunch of these algorithms in these 3 different stages. So essentially here, you try to detect and mitigate bias in the actual machine learning model using pre-processing, post-processing. And after we do that, you do a risk assessment. While you're doing that, we also give the choice for a standard and custom flow. Standard flow refers to what I just mentioned right now, and custom flow refers to the custom processes that certain companies might have placed that kind of gels well with their own culture and data science community that they might decide to proceed with. For example, in-house libraries or tools that these companies exclusively use that facilitates model building for them specifically. So we make way for that as well in the custom flow. So essentially, standard flow is our default. If you want, you can integrate your own process with custom flow. And finally, outcome involved. This is a familiar scenario in enterprise settings where you'd like to push updates to an already deployed project in light of new data or model. Or it might be a scenario where you want to deploy a previous model on a new test population. The issues here are a little subtler and different. For example, data distribution in your test population may be different from the training population. And even if the previous model was unbiased, we would like to make sure that the new iteration is also unbiased on the new data. For this kind of situations, we keep a separate pipeline to emphasize this industry-specific subtlety. And what we do is we first check for any changes between the previous data and new data. We do a bias detection, and then we do post-processing mitigation. So this is kind of similar to the ending part of model involved, but in the sense that this has its own specificity in terms of data change and the model already being deployed and potentially being a black box that you can't necessarily modify. Finally, this is a schematic of the SIP framework. I'd just like to highlight that there are different functions that are in there in each of these pipelines, and some of them are marked H, some of them are marked M. These signify that this is human level function, this is a human in the loop function, and this is a mechanized function. And as you can see, I pointed out the risk assessment steps in each of the pipelines, which are at the end of each of the pipelines. And if you don't wish to proceed in human risk assessment, you can just stop right there. Also, after the first pipeline, you can move on to either pipeline 2, pipeline 3, or you can just directly move to pipeline 4 based on whether the project is deployed. If it's deployed, move on to pipeline 4, which is the model involved pipeline, which is the outcome involved pipeline. And otherwise, you move to pre-model, then model involved. So in a sense, the progress through these pipelines is not linear. It starts from pipeline 1, then moves to 2 and 3, or moves to 4. Unpacking the human in the loop functions a little bit, these are the novelties of SIFT. This is the third novelty of SIFT, as I mentioned earlier. So in pipeline 1, Edge verifies similarity of past projects with the project at hand after using some kind of simple search mechanism to kind of shortlist the past projects. Identify sensitive categories. This is also done at human level after the first level of vetting. And the risk assessment. Risk assessment is always human. A human always decides at the end of each pipeline whether to proceed to the next pipeline. Pipeline 2, preparing data, feature engineering, or data filtering, things like that. Verifying and getting more data if needed. So for example, sparse group. There is a sparse group problem in the data. You don't have enough data on certain sensitive features. You then like to stop and move on, stop and get more data before proceeding. Dropping proxy features, risk assessment. Pipeline 3, only one human function, risk assessment. Pipeline 4, whether to retrain the model in terms of whether to retrain the deployed model and come back and re-verify or not, and risk assessment. So these are the human functions that ensure that quality is being maintained in the machine learning process. So we don't always leave things to machines. We would like to be involved as well in terms of taking crucial decisions in the machine learning process before actually the product gets deployed. And that's where things like policy, legal, and other teams come in. So, for example, risk assessment in pipeline 1 can involve the advice of legal and compliance to identify sensitive features. Verify, get more data may require approval from privacy or legal in terms of what data you need and whether you have the actual permission to access those extra data sets. Dropping proxy features. That can benefit from consultation from subject matter experts with different departments, like whether it is okay to drop these proxy features. And these guidelines are also can be reused in the sense that frequently answered question type things can be, so these experts, policy, legal, HR experts can be reached out from before, ask them that, hey, these are the questions that data scientists ask mostly, and then get their answers from the get-go. So to inform the data scientists a little bit in the beginning, and then let them reach out to the subject matter experts as needed. Finally, a little bit of an use case, how SIFT would work in an enterprise setting. Consider a targeted advertising setup where there is a promotional campaign for an early adopter model. For that, you'd collect some demographic data, some survey data, some customer information in terms of consumer segmentation, and then you'd get a list of consumers that you'd want to prioritize targeting a new product, prioritize discount for a new product too. And since this is a new project, there is no deployed project, there is no outcome involved. So you move from P1 to P2 and P3 in SIFT. So for P1, information gathering, you would initialize a new project and then obtain a list of similar projects. After the human consideration, you say that, okay, race, gender, marital status are the complete list of our sensitive features. Bias metric is disparate impact, which is pretty well known. Then you proceed through SIFT because the human intervention detects potential risk of bias since there are a bunch of sensitive categories. And then the next pipeline is pre-model, as this is not a deployed project yet. Pre-model begins, you prepare the data, do some feature engineering, and then detect sparse groups. You find out that there is an underrepresentation of non-white customers. So the team decides to terminate the project with 1 year timeout, which means that this project information will remain in our project database for 1 year. And within that time, if there is a new project comes, which is similar, we'll use this information. And then you exit SIFT after updating the project information. The bias history for this will be stored this way. Step 0, information gathering, nothing done in terms of detection and mitigation, but risk assessment indicates you want to go through SIFT. Then step 2, pre-model, bias features identified, bias detection function applied, and then the recommendation is get additional data. And then next is exit SIFT, team will collect additional data, project terminated. So that's the actual information that will be stored for posterity. Now suppose 6 months later, another team creates a new project with additional samples from the underrepresented group. Now what they do is add a pointer to the previous project, copy over the sensitive projects, and the risk assessment quickly verifies that by reusing the information. Then it again goes to pre-model. No statistically significant indicators of bias were revealed, like proxy features. There is no proxy features in terms of features being strongly correlated with the sensitive features. There are no sparse groups. There are no marginalized groups as detected by the specific statistical algorithms. And then the project proceeds to model involved. In-model involved, no bias detected in pre-model. And then the actual model is trained. After a train test split, the information for which is also stored. The test set accuracy is 77.6%, but then one sensitive feature shows bias. Finally, an in-processing mitigation method, which this is already well known in the literature, adversarial debiasing. This is applied, and no bias was detected in the debias model because the disparate impact threshold is by EEOC is 0.8 to 1.2. It was 0.79 for gender, so less than the threshold before. But after debiasing, it's within the safe threshold of 0.8 to 1.2. So risk assessment says that, okay, you're fine to go forward with the deployment. Project is scheduled for deployment. You add it to the project database. So this kind of gives an informed way of progressing through different stages of a machine learning project lifecycle. So the specific benefits of SIFT in this use case was the use of compliance guidelines to select the sensitive features, the fairness versus accuracy trade-off to actually see that, okay, how much performance hit are we taking to address fairness, the model reuse from older project, and the use of bias history to increase efficiency in doing this reuse. Finally, I'd like to end with a few pointers to operationalizing SIFT. As I mentioned, SIFT can be adapted to enterprise needs, but project managers have to be very aware of this, and they have to be incentivized to actually maintain proper project documentation. SIFT builds up on the past project information, so it is necessary to have that information documented in the first place. Finally, some cost-benefit analysis has to be done periodically to make sure that the cost of bias monitoring is viable in terms of financial risk metrics that are important to the company, and also forming rubrics of human oversight guidelines. So essentially the fact-style documents to kind of facilitate the human steps. And this can be done with by consulting with subject matter experts. And also, I mentioned there are a bunch of tools that are available to integrate fairness considerations in the industry, to integrate different bias detection and mitigation tools in the industry framework that also are those kind of tools and techniques can also be plugged into different steps in different steps of SIFT as required. So that's it from me. Thanks a lot to everyone for listening to the talk, and happy to take any questions.
That was Subhabrata Majumdar, Senior Inventive Scientist at AT&T Labs Research, sharing his presentation on a framework for industrial uses that address their organization's methodological and mechanization needs. He delved into how their approach benefited from prior experience handling security and privacy concerns, as well as past internal machine learning projects. If you'd like to watch more videos like this one, you can subscribe to the DSS Insider program, where you can see our complete on-demand video repository from a wide range of topics. Subscribe now following the link in our video description below. Thanks!